In this video, we're going to look at vapor pressure. Vapor pressure happens when a liquid forms a gas above that liquid. So it's different than evaporation because in evaporation, it's an open container. And so basically the molecules of the substance just keep escaping, okay? Vapor pressure happens in a closed container so that all the molecules stay contained within that. So this happens to every liquid, okay, that there's going to be some amount of gas above the surface. And same reason it happens with evaporation is the fact that some of these molecules in this liquid have higher energies than others. And so they're able to break that bond or this transition between being a liquid into the gas. But condensation also occurs when I have the gas is going back to being a solid, especially in a closed container. And so for any given temperature, the vapor pressure is constant. And so it's also, I should point out the fact that vapor pressure is substance and temperature dependent. Okay, so each substance will have a different vapor pressure at the same temperature, and each substance will have a different vapor pressure dependent on temperature. And so this next graph shows this. I'm sorry, not this next graph. Okay, so this is showing here what happens. So the rate of vaporization, so going from a liquid to a gas, is solid. As long as I have liquid present here, then this process is going to be solid for a given temperature. I have to have gases first in order for condensation to occur. So this starts out at 0 and works its way up. As I form more gases, then the rate of condensation occurs. And then at some point, the number of molecules going from a liquid to gas per unit time equals the rate of gas going to liquid per unit time. And when that happens, this range right here is when my vapor pressure is constant. Okay? And so that will eventually happen here. The fact that initially all my molecules are becoming gases, but as soon as I start to increase the number of gases, some of them go back to being liquid. And vapor pressure happens at the point where the rate of evaporation equals that of the rate of condensation. This is the slide. This shows you that different substances, diethyl ether, chloroform, and carbon tetrachloride, these three are organic molecules, okay? And you'll notice that, so diethyl ether here has the highest vapor pressure at any given temperature, okay? And so it's going to be the most volatile, meaning the fact that it's most easily to become a vapor, all right? Chloroform there. And so all of these increase with temperature, okay? But they all have their unique lines. And then this one is water, okay? So all vapor pressures increase with temperature. Each substance has its own unique vapor pressure profile, if you will, okay? So vapor pressure is constant due to the fact that the vaporization and condensation happen at the same rate, okay? What's different is boiling, okay? So vaporization happens at any temperature. Oops, I don't know why it's not writing right there. At any temperature below boiling and above freezing. Okay. Boiling is substance dependent. I say boiling point, meaning the temperature. So it has to be, the substance has to be at or above that temperature in order for boiling to occur. And boiling is different than vaporization because vaporization happens only at the surface. Vaporization, I can't spell anymore, only occurs at surface. So the molecules are only leaving from the surface. Boiling happens throughout solution. Or liquid. I'm going to say liquid. Little difference, but liquid or solution typically means a mixture of stuff. And so that's what you see here. So for boiling, I form these gas molecules inside of the liquid. Okay, and those gas molecules, so this liquid has become a gas right here, and then these will rise up and will escape. If you ever watched a pot of water getting ready to boil, typically the heat source being on the bottom, you will actually see the bubbles form on the very bottom. On metals, it's really easy because it's not perfectly smooth. Okay, so it gives this spot. But once it's what they call a rolling boil, then the bubbles are forming throughout the whole solution. Okay. All right. So freezing versus melting. Freezing point is the temperature at which the liquid changes to a solid. A melting point is the temperature at which a solid changes to a liquid. These two occur at same temperature for a given species, or a substance, for a given substance. In other words, water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. Water melts, or ice melts, at 32 degrees Fahrenheit or 0 degrees Celsius. Okay? So the melting point and freezing point temperatures are always identical, and are physical characteristics that we can use to identify them. If you go into organic class, you'll see the fact that they do that. And so in this, the other thing is that this is a glass of just ice, and the thermometer reads at 5 degrees Fahrenheit. As soon as some of that ice begins to melt, it raises up to 32 degrees. As long as any ice is present, okay, then I have it at 32 degrees. The temperature only starts to rise above 32 once all the ice has melted. Okay, I'm going to be able to see that on the next slide. So this is what they call a heating curve for water, or temperature curve for water. Okay, so this is ice, and this is the ice warming up. So this is just the amount of heat or the amount of energy added. Okay, and it reaches 0, and it stays at 0 until all the ice is melted, and then the temperature can raise up in the liquid, and it stays at this temperature here of 100 degrees Celsius until all the liquid is gone, and then I have steam, and I can raise the temperature of the steam. Okay, so this is in a closed container, if you will. All right, and in this I have two terms. I have the heat of fusion, which is the amount of heat required to melt a solid, and so that's going to go from this point here to this point here. Okay, and so however many kilojoules on this, it looks like it's about 5 kilojoules per mole. Okay, and I also have the heat of vaporization, which is the heat needed to change a liquid into a gas, and so that's going from here, which is about 15 kilojoules, to over here, which is about, say, 53. We're going to say 55 just because it's easier, is at 40 kilojoules per mole. Okay, And it's important to know that the heat of vaporization is always greater than heat of fusion. Okay, so quantifyingly, and that's because what's happening is that I have a solid down here, so it's very ordered, going into a liquid, which means it's just less ordered, and it's really hard to draw something less ordered when it's still close together, okay? But they're moving around, and so all I need to do is take it, give it enough energy that these molecules are willing to move around. Versus down here for heat of vaporization, I'm going from my disordered liquid, and it's really hard to draw something disordered, to a gas in which the molecules are really far separated. They're no longer touching. So not only do I have to then get them moving faster, I have to move them fast enough so that they're willing to separate from each other. And so that's why the heat of vaporization is always much greater than that of heat of fusion. And we will continue this in the next video.